Okay, dear students, thank you very much for watching my TV, my channel, Biopharmaceutics Mentor. And now today our next topic is very interesting topic of the biopharmaceutics to imagine what are the size of my even weight of my eye, weight of my lungs, and if I want to calculate okay weight of my heart, and I want to calculate the clearance of any drug which is not given to me, only given to the small animals, then how is it possible for me to calculate what effect of that drug on my body? This is the basic concept to understand this concept of the log graph. Today our topic is log log graph. Okay, in our previous videos we have rectilinear graph, semi-log graph. Now it's a series of the third series of the graphical representation which is being used in pharmacokinetic studies is the log graph. In case of log graph, as the name mentioned here, both of the scales would be in the logarithmic scale. In case of rectilinear, there were no any type of the log. But in case of semi-log, the graph say y-axis was on the logarithmic scale and x-axis was on the rectilinear scale. But here we have both scales of the log graph. Log graph means x-axis and y-axis, both values should be written in the form of logarithmic scale. Scale would be on the logarithmic area. Once again, uses of the log graph. First of all, we have a empirical approach to calculate our different parameters of the drugs. For example, I want to calculate the clearance of methotrexate drug, which is anti-cancer, on my body. And I have not performed this experiment on myself. Just I want to predict this type of the concept, this type of the clearance by using the data of the small animals. And by taking the small animal, we have the difference of the two. For example, in case of small animals, we have clearance of the we have the molecular different weight of the small animals, and having the different sizes of the organs, and have the different areas of the uh, body size of the animals. Then we will predict our behavior of the particular drug by using the log graph. So in case of empirical approach, we will which is another name of the allometric approach. In allometric approach, we predict any type of the data which we are just assuming that same concept would be in our body, and in case of this concept would be applied especially in our cases. Okay, let's start with the log graph and its construction first. How to construct it? First of all, I will make the difference of the three different graphs. For example, in case of rectilinear, we were having the same boxes. Just I have already mentioned in my previous videos. Big box 0 and 2, then having the very equal sizes of the small boxes on y-axis as well as on x-axis. That was the rectilinear. But when we move toward the semi-log, in case of semi-log graph, we had different cycles, and cycle contains the different lines. First line was very broad, but with the passage of time, that was these lines having the difference, the smaller space between them, and on x-axis, our same boxes were there by you just like to the rectilinear. So this was the concept of our semi-log graph. That was rectilinear, and this was semi-log. Okay, what would be the log graph? In case of log graph, we will have to take the logarithmic scale not only on y-axis but also now on x-axis. So in case of log graph, we have this type of the profile. Okay, this one, these are the basically cycles, and cycles contains the different areas. For example, same having the big difference from these lines. And then another way, we have another cycles. In case of cycles, we have these lines just like to be the logarithmic scale. It would be very much clear when we make some type of the numbers here. For example, in case of rectilinear, on y-axis we are starting with the 0, and in case of semi-log we are once again on x-axis we are starting with the 0, 0, 2, 4, 6, 8 and so on. But in log-log graph, we will never start from the 0, because just like to the semi-log graph on y-axis, we are not starting with the 0. So here we can also write the 0 to maybe 20, 40, 60. And in case of here, we have to write the 1, 10, then 100. This was the profile of the semi-log. But in case of log-log, what we will do? We will start with the, say, the 1, then our next is 10, then 100, then 1000. Remember, on x-axis, we will have the same logarithmic scale. For example, we are starting with the 0.1, then 1, then 10, then 100. So there is a big difference between these three types of the concept. Remember, in case of rectilinear graph, we have prepared y is equal to mx plus b, if profile was this one. And here, if profile of this one, then ln y is equal to mx plus ln b. But when we are moving toward the log-log graph, now we are taking the logarithmic scale of x-axis also. Now our equation would be ln y is equal to m ln x plus ln b with the same line. Why we are using this? By the difference. In case of rectilinear, we have only simple concept without any log. Y is equal to mx plus b. And in case of semi-log, we have logarithmic scale ln y, ln b, because these both are on the y-axis, so we have the logarithmic scale. But here ln y, ln b on y-axis, but ln x is the on x-axis. So there is a big difference. Now our concept is, can we draw an animal having the 50 gram weight and just like us having the 70 kg weight? Means where is 50 gram and where is 70,000 gram? So can we draw on a single graph? Our answer is yes, we can. Why we can use the semi-log graph? Why? How? We can use this type of the graph by scaling in the logarithmic scale. When we making on the power of 10, then it means we are just getting the difference of the 1000, even 10, then 100, then 1000. Then we can even plot the 50 and 50,000 on the same scale. This is a very interesting information which we can get from the log-log graph. Now, another step of our studies, our process is, now we will have a data and then we will plot it on the on the log-log graph. Then we calculate, okay, unknown values of our data. So data is, in case of log-log graph, now we have body weight on x-axis and other data, cardiac rhythmia, cardiac rhythm on y-axis. So if we have body weight 10 gram, then cardiac rhythm is 0.213. If we have body weight 60 gram, then it's 1.442. If we have 1800 gram body weight, then it's 2.234. And if we have 7000 means 7 kg of the weight, then we have 3.46. And if we have 50,000 means 50 kg weight, just like us, then it's a 4.2. Okay, we can say we have cardiac rhythmic results on, say, 10 gram, maybe mice, small size. 60 gram, maybe rat, but with very small size. 1800, we can say, okay, maybe rodents, rabbits. 7 kg, we can assume that maybe some type of the dogs, animals, and then 50 kg, like to be a human. Okay, when we make some this type of the graph, the data, then we will have to move toward the x-axis on y-axis. On x-axis, now we have the minimum 10 and maximum 50,000. Now we will have to move toward from the 10 to 50,000. Okay, start with the 10, for example, 10. Okay, we can start with the 1 here, 1, then 10, then 100, then 1000, and in our 10,000, and then 100,000. These are the scales just like to be the our logarithmic scales. These values on the x-axis. On the y-axis, we have minimum value 0.213 and maximum 4.26. So we can write here, okay, start with the 0.1, then 10, 1, then 10, then 100. Same like to the semi-log graph, we will have to plot the same points. For example, we have the value at 10, we have the 0.23. At 10, we have the 0.23, 0.23 is here. Okay, at 60, we have the 1.42, here is 60, and 1.42, maybe this one. And at 1800, we have maybe this point, and then this point. Okay, we will interpolate these points. Now our equation would be different. I have already written here, ln y is equal to m ln x plus ln b. On x-axis, we have weight, and on y-axis, we have rhythmic score, cardiac rhythmic mia of the different species. Now our concept is we want to calculate the cardiac arrhythmia of the patient having the weight of maybe 60 kg or 40 kg. Then how it is possible? Then we can say, okay, it's very simple. First of all, we have to calculate that value, that is B. Now I will write. Okay, very important concept in this concept in the log graph is y-intercept. So everything is okay now. Now we are moving toward the our y-intercept. For example, we have this type of the profile, and our need is to calculate y-intercept because our equation is ln y is equal to ln m ln x plus ln y naught or b. Okay, when we have this type of the profile, for example, I will make this line. Okay, now in our previous practice, what we were doing in our previous practice, particularly in rectilinear, we are just taking the extrapolation of this. Okay, observing the value on x-axis at 0, that was 3, it's y-intercept in case of rectilinear. But in case of semi-log, at 0, for example, this profile is this way, then here is 1, we can say here is 5. So at 0 on x-axis, value on y-axis, which is 5, is the y-intercept. I guess this concept is till now clear. Okay, when we discuss the log graph, in case of semi-log, we have the 0. In case of rectilinear, we have the 0. But in case of log, we have no any type of the value of the 0. So we will assume that, okay, where is the 0? When we take the log of this 1, and when we take the log of 1, that would be equal to 0. So at that point, we will assume that this time is the, for example, is 0.1, it's 0.5 would be the y-intercept. Okay, I will make another example for the clarity of this. I will make the line. For example, we have the scale is this one, starting with the 0.1, then 1, then 10, then 100, and then 1000. This is our scale on x-axis. Okay, we will search where is 0. Where 0 is there, where is the 1? For example, in this scale, now at this point, log 1 or natural log 1 is equal to 0. At that point, the value of y-axis, for example, it's 0.1, it's 1, and it's a 2. So this 2 is the y-intercept. Once again, I will repeat this concept. In case of rectilinear, we are searching the value on y-axis when x is 0. We have. But in case of semi-log, we are searching value on y-axis when x-axis is 0. But in case of log graph, we have no any type of the 0 value. Now we will apply the log values. Where log value 1, where the value number 1 is, for example, we started point of 0.1, then 1 is here. So at that point, we are assuming that the value is 0. So at 0, the values on x-axis, y-axis should be called as y-intercept. This is the basic concept for the y-intercept. Thank you very much.